This is lecture number 2 of the course Engineering Mechanics. In the last lecture, we defined velocity of a particle with respect to a frame. This quantity was defined as the limiting value of the quantity that I have written here. RPO is the position vector of the particle of interest P. This is at time t, and then the same particle would move to another location at time t plus delta t, and we get another RPO, another position vector. Those are the quantities that are appearing here. In this definition, O is a point fixed in frame F. We defined another kinematic quantity, kinematic vector, the acceleration of same particle, of particle P, with respect to the same frame in context. We will use the symbol A subscript P bar F to denote this quantity, and the definition of this quantity is what I am writing on the screen. Tied to the frame F. This can also be called as rate of change in the vector VPF as seen by our observer who is tied to the frame F, which I showed earlier on the screen. This observer. We can also write APF as d dt of VPF with respect to frame F. VPF, on the other hand, can be written as rate of change of RPO vector with respect to F. Thus, APF can be written as the second derivative second derivative of RPO, and both derivatives have to be taken with respect to frame F. We will allow ourselves in this course to write the two derivatives in a more compact manner as this, but then our understanding is that both derivatives are with respect to the same frame F. I am writing F only once here, but we are agreeing of this implicit understanding that even though I write single F there, both derivatives involved here are with respect to F. We will also allow ourselves to use another shorthand. For VPF, we can write VPF as this. So instead of writing d dt, we will put a dot, and that will be considered as an acceptable notation. Following this shorthand notation, APF can be written as single dot, where again the implicit understanding is that both derivatives, there are two derivatives involved here of RPU. One is this frame F, and another derivative is represented here. Both derivatives are with respect to the same frame F. We can also write APF, and sometimes we may just write APF as this. Two dots means double derivatives, and this F, even though appearing once, again the implicit meaning is that both derivatives are with respect to F. So all these are acceptable notations for our course. It is important to note that the acceleration vector of a particle with respect to F is precisely this quantity. To avoid confusions, I want to present a scenario in which I have two reference frames. Say one is F, the other is G. Suppose both the observers from these two frames are observing the same particle P. They have their own origins fixed to their own frames. Now suppose this is the position vector that the first observer from frame F is reporting, measuring. He can define a quantity like this, which will be the velocity of particle with respect to frame F. Now suppose one computes a quantity like this. What is this quantity? Now if you look at the SI units of it, it will indeed be meters per second square. But keep in mind that the presence of two different frames makes it a quantity which is not the same as this is not the same as APF. For that matter, this quantity is not even APG. So this quantity is neither the acceleration of P with respect to F, nor it is the acceleration of P with respect to G. It may be a mathematically viable quantity, but in our study of particle kinematics, or even for that matter rigid body kinematics, we do not give this quantity any importance. It does not have any relevance for us. If such a quantity is indeed appearing, this would not be considered to be an intentionally defined quantity. Most likely it is a mistake. So please keep this in mind, that for APG to be, the acceleration of particle P to be sensibly defined, both the reference frames should be F. Another definition, another useful definition in our study of kinematics: a long phrase, velocity of a particle A relative to particle B and with respect to frame F. We will come across this quantity when we start dealing with the angular momentum of a rigid body. How do we define this quantity? First, I put the symbol. This quantity will be denoted by this symbol, where this is a point, this is also a point, and this has to be a reference frame. This is defined as the difference between the velocity of point A with respect to F and point B with respect to F. Similarly, we define acceleration of particle A particle B relative to particle B and with respect to frame F. We denote this quantity by the symbol A subscript AB bar F, small a subscript big A big B bar F, and the definition is this, similar to what I had here. Instead of velocity, I have acceleration. Now note that we are taking difference between two velocities. difference between velocities of 2 points, and the mention of frame F is very important here. Suppose we have two reference planes F and G, and there are two particles AB which are being simultaneously observed by the two observers. Do keep in mind that in general, the relative velocity of point A relative to B with respect to F will not be the same as velocity of A relative to the same point B and but with respect to another frame G. Similar inequality in general will hold for the acceleration as well. Let me give an example. Let this big disk represent frame F, and then there is a small disk which I call as frame F. Suppose this smaller disk is rotating with respect to the larger disk. Smaller disk, which is a frame by itself, rotating with respect to frame G. And O prime, which is fixed in F, and O, which is fixed in G, are coinciding. Let's assume that for simplicity. This is center of larger disk. This is the center of the smaller disk. And we are having a sort of a top view of the two disks, right? Now let us consider 2 points A and B. A and B are both fixed in F. Further, the distance of A from O prime is the same as the distance of B from O prime, and let that distance be R. And let this angular velocity or this rate of rotation be omega. Let's have two unit vectors so that I can express some vectors in terms of them. What is VAF? 0, because A is part of F. What is VBF? That is also 0 because B is fixed in F. And thus it follows that ABF will be VAF minus BBF, and that must be 0. In contrast, now let's have a look at what is VAG. VAG will be omega R minus J at this very instant, right? The disk is rotating counterclockwise as seen by the observer fixed in G. What will be VBG? VBG will be plus omega R times G. Now if you try to find the velocity of A relative to B with respect to G, this is going to be minus omega rj minus omega rj. That turns out to be minus 2 times omega rj, which is clearly not 0. Thus I have shown a case in which you do not have velocity, the velocity of A relative to velocity of B with respect to two frames being entirely different from each other. Having now defined velocity of a point with respect to a frame, acceleration of a point with respect to a frame, we now want to move to a new topic, which is coordinate systems. Coordinate systems. What is a coordinate system? I will use this acronym CSYS. This is the first clarifying statement I want to make, that a coordinate system is not the same as a reference frame. Sometimes students get this impression that a reference frame itself is a coordinate system. No, that's not true. These two are different concepts. Yes, many times we do have a reference frame and there is an embedded fixed coordinate system also shown on the diagram, and that coordinate system shown on the diagram is used to express various vectors of interest. Even though we see many figures which has a reference frame and a fixed coordinate system, that does not make a coordinate system the same as a reference frame. Please keep in mind. I will write a few more statements with which I hope we will be able to understand what exactly a coordinate system is and what its utility is. Coordinate system is comprised of a point, also called the origin of the coordinate system, and three non-coplanar vectors. Unit vectors. Even though it is not necessary for the three non-coplanar unit vectors to be mutually perpendicular to each other. Many times we do work with coordinate systems in which these three unit vectors are mutually perpendicular, and in that case the coordinate system is called the orthogonal coordinate system. In this course we will be using three different types of orthogonal coordinate system. First is Cartesian coordinate system. Now Cartesian coordinate system can be frame fixed or not, or partially fixed to a frame, or not at all fixed to the frame. To the frame in context. I will explain the meaning of these phrases in a little while. What do we mean by frame fixed Cartesian coordinate system or a partially fixed Cartesian coordinate system or a not at all fixed Cartesian coordinate system? I will elaborate on that. The second type of coordinate system which we will use in this course is the cylindrical polar coordinate system, and the third one is path coordinate system. The pertinent question here is, why do we need different coordinate systems? Why do we need a coordinate system to begin with? And why do we need to be aware of different types of coordinate system? Right? These two are pertinent questions. To begin with, why I need a coordinate system, and even if I need a coordinate system, why are there different types? The answer to the first question is, we need a coordinate system to be able to express various vectors like VPF, APF in terms of the native unit vectors of a coordinate system. The second advantage of using a coordinate system is coordinate systems helps us perform vector algebra in a more easy manner. For example, if there are two vectors and I want to add them, this is vector A, this is vector B, how do I get A plus B? Now in our school we must have studied that there is a triangle law of vector addition which helps us get this A plus B vector. In this triangle law, what you do is you put the tail of the second vector on the head of the first vector, and then you try to make a triangle starting from the tail of the first vector to the head of the second vector, and then this new line segment with its magnitude and direction denotes A plus B. Now this is a possible way of vector addition, but it is very geometric in nature. You really have to draw lines and then add them together. In contrast, you consider a case in which somehow I can write a vector in terms of 3 unit vectors like this. These are 3 unit vectors, and these are scalar components of vector A along E1, E2, E3. Similarly, I can write B in terms of its scalar components and the same unit vectors E1, E2 and E3. Now if I have to add the two vectors, it can be done in the following manner. We all are aware of this. Since the 3 unit vectors are mutually perpendicular, the resulting vector can be expressed in this manner. So component-wise acceleration has been, component-wise scalar addition is possible. Compare this with the method here. This is, as I said, is very geometric, and here it's more arithmetic like. This feature makes this method more attractive, especially if you have to perform vector additions or even other vector operations like cross product or dot product on a computer. This method of using a coordinate system and adding or performing operations component wise in this manner would be easier than using a geometric method. So this is the reason we choose. This is the reason why coordinate system is useful. Now, having answered the first question that I raised earlier, why do we need a coordinate system? Now I want to answer the second question, why do we need to be aware of different types of coordinate system? Why different types? Depending on the given information, depending on the available information, one coordinate system may be preferable over another coordinate system because the other coordinate system, because the first coordinate system may require us to use less algebraic lesser number of algebraic steps to arrive at the final required answer. Okay, that's why we need different coordinate systems. I mentioned earlier that we are going to study three types of coordinate systems. In this course itself, we will see some examples in which solving a problem using a Cartesian coordinate system may involve lesser number of steps. However, in another problem, you may find that if you try to force yourself to use a Cartesian coordinate system to find a vector, say velocity or acceleration of a particle, it may require more steps compared to if you just choose the cylindrical polar coordinate system. So our choice of which coordinate system we will use is governed by which will involve lesser number of algebraic steps. However, please keep in mind that if you are ready to perform many algebraic steps and you don't bother about it, you don't bother about the efficiency of your solution procedure, then you can continue to use one coordinate system in your entire life for all problems. However, that is not recommended. Why to waste our time and energy sticking to only one coordinate system just for the sake of it? We don't do that. And that is why there are different coordinate systems. Also keep in mind that I am listing here three coordinate systems. There are many other coordinate systems available. In fact, one can go ahead and define his or her own coordinate system. Nobody stops us. However, these three are the more popular ones, and thus we choose to study these three in this course. So let's look at the Cartesian coordinate system in more detail now. As I said, Cartesian coordinate system can be used in three versions. One is the frame fixed Cartesian coordinate system. When I say frame fixed, what we are referring to is a situation in which origin of the coordinate system is fixed to frame F. This is the frame F. And the three unit vectors are also fixed in frame F. All these conditions are satisfied. Then we call the coordinate system as Cartesian coordinate system is frame fixed. Note that if E1, E2 and E3 are fixed in frame F, then whenever you come across such derivatives, time derivatives of these unit vectors, you can set them to be 0. While performing various algebraic operations, you may come across these terms, and they can be all set to 0 if you are dealing with a frame fixed Cartesian coordinate system. Now note that the way I made this coordinate system here, I have used x1, x2 and x3 symbols. Now these are the scalar coordinates. These are all scalar, set of scalars, scalar set. These are also called the coordinates of an arbitrary point P. Right? So P can be a point here moving in space with its own mind. At this current time instant, these three scalar, ordered scalar set, order matters. They are called the coordinates of an arbitrary point P while using Cartesian coordinate system. In fact, we will use a notation to denote this coordinate system, and this is the notation. This is the name of our coordinate system. Now the first letter appearing here, it denotes the origin of coordinate system, right? Whereas these three, I have already said, they are the scalar set, and they make an ordered scalar set, and they are the coordinates of an arbitrary point P. You can write it here. And E1, E2, E3 are the three mutually perpendicular unit vectors of our Cartesian coordinate system. Okay. Now note that using x1, x2, x3 and E1, E2, E3, I can write the position vector of point P measured from O. This is our PO. That can easily be written as this. Okay. I want to go back and also describe what what are the other possibilities of having this coordinate system, Cartesian coordinate system. Partially fixed. What would we mean by partially fixed coordinate system? In this case, it may happen that O is fixed to frame F, but E1, E2, E3 are not fixed, are not frame fixed. This will be a partially fixed coordinate Cartesian coordinate system. So you allow E1, E2, E3 to change their direction as seen by the observer fixed in F, but the origin is still a point fixed on F. We will see later when we look at the dynamics of rigid bodies, there may be a need to have such a coordinate system. Lastly, I want to describe what is not a fixed Cartesian coordinate system. Not a fixed Cartesian coordinate system. In this case, O is not fixed in F, and even E1, E2 and E3 are not fixed in F. In that case, our Cartesian coordinate system has no association, no fixation, no direct relationship with the frame F. It neither has its origin fixed there, nor its unit vectors are fixed to frame F. So these are the different possible ways in which a Cartesian coordinate system can be utilized. Now let's focus our attention entirely on a frame fixed Cartesian coordinate system. And I want to know the expressions of BPF and APF using this frame fixed Cartesian coordinate system. Okay, let me redraw here my Cartesian coordinate system, which is frame fixed. Okay, how do I get VPF? Now VPF I know is ddt of RPOF, where P is this point which is currently having its coordinates as x1, x2, x3. Right? I'm going to utilize product rule of differentiation now and get these 6 terms. Right? We get these these 6 terms. Having written these terms, I realize that since E1, E2, E3 are all fixed in F, means that the derivatives of these unit vectors must be 0. After all, the coordinate system itself is frame fixed. This implies that BPF will have simply 3 terms, which are these. However, you note that these terms are derivatives of all scalars. x1, x2 and x3 are scalars. It means that I really do not have to put this baggage here. After all, the time derivative of scalars, or the rate of change of a given scalar, is always frame dependent. So we can simply write this as right, which we can also write in a shorter form as this, where a dot on the top of a scalar means its rate of change in time. So this is the expression of BPF in a frame fixed, when I am using a frame fixed Cartesian coordinate system as my working coordinate system. And by the phrase working coordinate system, I mean I am going to express all my vectors of interest using that coordinate system, right? Next, I want to derive the expression of APF when the same frame fixed coordinate system, frame fixed Cartesian coordinate system, CSIS, is my working coordinate system. To get APF, all I have to do is to take derivative of the expression that I derived above. So by definition, this is what the acceleration of the particle P with respect to F is. I subject this expression to a derivative. Again, using product rule of differentiation, you will get 6 terms here, but three of those terms will be 0, and those will be terms like this. These 3 terms will be 0, and thus one can arrive at the expression for APF. And now I am going to use 2 dots to denote the second derivative of a scalar. Right, etc. So this is my expression for APF. These expressions, which I now mark as 1 and 2, will be very handy when we try to solve some problems of interest where the velocity and acceleration of a particle need to be found.